Hi everyone, my name is Jacob Thoma and I work on Psyche Flight Software at JPL along with Armen Arslanian. Armen and I will be talking about the dual string flight software that Psyche uses for data transfer and synchronization. Slide. So we ported a heritage design which has been used by Cassini, the Mars rovers, and other missions to a time and space partition flight software architecture, which Psyche uses. We consolidated some of the modules used in the original design and adopted a new division of labor across these modules. It was consolidated into pretty much two modules, a higher level one called Cross-String Manager, which initiates transfers and schedules the bus transactions, and a lower level manager called Remote Terminal or RT Manager, which is more of the driver level interfaces that talk to the actual RT hardware. We also built a custom data transfer protocol on top of 1553 that allows us to transfer files with some level of autonomousness at stopping transactions if anything looks wrong or data stops being transferred properly. And finally, the protocol can transfer files, send cross-string commands, and perform PCI pseudo-DMA operations all at the same time. Slide.
So a little bit of a background on the Psyche Flight Software. It's a branch off of the JPL, what we call the Flight Software Core product line. The main difference between this and our heritage flight software is that FCPL uses time and space partitioning, which some of you may already be aware of and familiar. The modules are basically divided into functional categories and areas, and these are called partitions. There's the two concepts of space partitioning and time partitioning. With space partitioning, each partition has their own virtual address space, and they can't access each other's memory unless there's an explicit shared memory region. And for the time partitioning, each partition is allowed a certain amount of time, which is defined at design time. And they run in a 16 hertz cycle, which is called a minor frame. So there's a picture below that gives an example here. The cycle in this case is 16 hertz. And in the example, we have 4 partitions. And as you can see, with partition 3, it takes the longest, and partition 4 is a bit smaller, so that takes less time. But in the next cycle, it's the identical cycle of partition 1, 2, 3, and 4 running in the same order. This is a background of the hardware that we use on this mission. We have 2 command and data handling subsystems. They host the flight software, and these are block redundant pairs, so essentially what we call dual string. And in this case, the flight software that runs on each CNDH controls a set of hardware signals that are used by our 2 modules for the dual string flight software. And these signals are triple modular redundant for added fault protection, and also for safety. The signals that go to the opposite string are read back from the current string that sends the signals, And this is an added check to make sure that what is intended is actually what is going out to the other string. And it's the same for CNDHB. The flight software that drives those signals also is read by the same string to make sure that what is intended is actually being sent to the other string. So our main form of communication is MIL standard 1553B. This is the standard 1553 that has been used for many, many years. So previously we discussed that we have two command and data handling subsystems, where one is the primary and the other is the backup. And sort of translating to this diagram, we always have a primary bus controller, and we have a backup bus controller that can take over if needed. And we have many remote terminals on the spacecraft, many devices that are remote terminals. And we will talk about how the one CNDH is always the bus controller and the other is an RT. And that's how we communicate with each string communicates with each other. And some important points here is that we use this for the data transfer in between the two strings, as mentioned. And our mission, Psyche, uses a static bus schedule. So this has statically sized windows for transactions, and in each minor frame, in each cycle, the same group of transactions go out. So this is why it's very deterministic.
So to give you a little bit more of a big picture of how everything is connected, this is the data path for doing something like transferring a file from one string to the other. You can see the first string, which is the prime string, which I'll talk a little bit about that. Prime is the terminology we use for the string that's designated as the bus controller, and the other flight computer is designated as online, which basically just means that the flight software is running and it is not the bus controller. So it's sitting there listening on its RT for commands or synchronization messages from the prime flight computer. Both strings are capable of being the bus controller or the remote terminal, and the primary string is the bus controller and the backup is the RT. And the prime initiates the bidirectional transfers and commands. So you can see here a command, cross-string command, would initiate in-flight software on the prime string and schedule something using the 1553 bus controller, which is received by the RT on the other flight computer, which then transfers that message to flight software, and flight software could maybe go get a file from the file system and deliver it back using our custom file transfer protocol. Slide. So another way the data path can work is if flight software is only running on the prime string, we can still use a pseudo-DMA PCI functionality to access memory on the backup string. And that will work whether flight software is running or not on the other flight computer. Next slide. So here's a picture of the flight software stack showing Cross-String Manager being the higher level module on the prime side and the online side, and it's talking to other service modules such as command service and file service. On the prime side, it's the lower level module is the bus controller manager and driver, which allow it to schedule those bus transactions in the static schedule that Armen mentioned. Then it goes over 1553 to the RT on the online flight computer, where RT manager receives the message and then sends it along to cross-string manager, which then talks to the appropriate service modules to possibly save file to the file system on that flight computer, or notify command service that it has received a command from the prime string. Next slide. So a little bit more about cross-string manager. Like I mentioned, it's running on both strings and performs different functions based on which string we're on, whether prime or online. So the prime cross-string manager coordinates the higher level data flow between the two compute elements. It initiates all operations, including file transfers, data product transfers, and cross-string commands. The online version is kind of sitting there waiting for requests that it will receive through the abstraction layer of RT Manager. So it doesn't have to understand the complexities of the actual transfer. It can just do something like receive a request to see if a file exists on the file system on this side. It also handles string arbitration, and what I mean by that is the decision to become a prime string, basically to become the bus controller, and it makes the decision based on preference over string A or B, whether the other string is already prime, and then also a flag that forces it to wait in online state and not become prime. It also coordinates time synchronization between the two strings. Since our time synchronization is centered around a periodic 1553 mode code for finer grained time sync, and then another 1553 message which contains the seconds of the prime string for coarse grained time sync. Now Armen will talk a little bit about RT Manager.
Yes, so as the name suggests, RT Manager is Remote Terminal Manager. It manages the 1553 remote terminal of our command and data handling subsystem. At initialization, it configures the transmit and receive subaddresses as well as mode codes, and it monitors the hardware in every flight software cycle. And by hardware monitoring here, we mean that in each cycle of execution, we check for hardware errors and take the appropriate actions to minimize the downtime of the RT. Its remote terminal's main purpose is to facilitate the communication between the primary and backup CNDH over the 1553 bus. It performs the data transfer based on the custom protocol that we implemented. It notifies cross-string manager that the prime string is requesting a data transfer, and it also passes the data to cross-string manager in a format that is ready for the backup string to process. It's also capable of handling commanded or unexpected termination of data transfers, or if a termination happens when we swap strings. And RT Manager, again, will provide continued support for cross-string communication and minimize the downtime of data transfers.
So we also created a custom data transfer protocol, which is built on top of 1553 to transfer larger files, since 1553 can't transfer that much data at one time. So data transfers begin with a request, which sometimes includes metadata like the file name that it's requesting, or if it's sending a file to the online string, the file name that it wants to write to. Sometimes it will wait for confirmation that a file exists on the online string before then proceeding with the transfer. So that would be if it was asking for the online to send a file to the prime. It uses pipeline data and acknowledgement. So we're ACKing each RTI of data as it comes with an incrementing sequence number that is confirmed on both sides of the transfer. So both cross string manager and RT manager know exactly how many transactions and transmit notifications there should be for a certain size file transfer, since the file size is agreed upon at the beginning. So if anything is missing or incorrect or stale, either side will abort the transfer. It does take about 20 minutes to transfer a max-sized file, which is about 4 megabytes, but we are not optimizing for speed, so that's okay. And then we divide work across subaddresses. So there's a separate subaddress for data and a different subaddress for the status and acknowledgement, which Armen will talk about on the next slide.
Yeah, so a little bit of more detail about the subaddress work division. As we mentioned before, we have various types of transfers we can do between the two strings. So that involves file transfers, commands, and also low-level DMA reads and writes, and a spacecraft health report. So we decided to divide them in the following functional categories. As you can see, the data and acknowledgement and status messages are on separate subaddresses, and the same goes for file transfers, commands, and for command completions, this is asynchronous, and it can always be reported. This is actually a pulled message that is separate from the actual command data and acknowledgement for the command transfer. This method will also let us know that if we sent a command to the backup string and it never responded, this is a method we came up with that'll help us determine that. And it will also, which is important to mention, it'll also let us send other commands to the backup string and not block that act of sending commands. So a very useful feature of dividing these subaddresses was that we had a bus log during our implementation of this flight software, and it was very easy to diagnose failures and observe what the exact failure was because of the divisions of subaddress. And it also sped up development because of the same reason. And our whole scheme about checking received versus expected messages on both the primary and backup strings also sped up development. And we hope that this will be useful for in-flight anomaly investigation as well. If one side reports that there was a termination of transfer of data, we know exactly at what step of that data transmission it was terminated, and we actually know what the reason was and what the expected outcome should have been. So that'll help us greatly in anomaly investigation. So to recap, we talked about how we took the heritage dual string design and applied it to the time and space partitioned new flight software architecture. We mentioned that we can transfer files, send cross-string commands, and perform PCI DMA operations all simultaneously from the primary string to the backup. And we do this via 1553, as we showed in a few diagrams. And we're able to determine which string is prime and which string should be the backup based on the hardware signals that we showed in the earlier in this presentation. And now Jacob will mention about what future dual string missions could do and what we can do to improve this custom protocol.
Yep, so if we were going to change anything in a future iteration of this dual string flight software, one thing would be to shift the cross-string manager, remote terminal manager abstraction layer slightly. And what I mean by that is on the online string, cross-string manager is fully abstracted away from the complexities of our transfer protocol. And it basically can just receive simple requests from remote terminal manager without really having to know what's going on the bus, like read this file or write this file or get a certain data product. But then on the prime side, cross-string manager is not abstracted away from any of this and has to understand the kind of RTI by RTI timing and handshaking of the data transfer, which kind of adds more complexity for sure on the prime side. Another thing we could do is simplify the acknowledgement scheme we used in the custom protocol. So we used the separate subaddress for status and acknowledgement, which was a good idea, but there are some ways we could have kind of played to the strengths of 1553 more. So instead of using bidirectional ACKs, we could have pulled the status register and used the presence or absence of transmit notifications on the online remote terminal to determine if anything had gone wrong on the prime, rather than have an explicit ACK. And then lastly, in a super ideal world, we could have a more sophisticated protocol level retry, kind of similar to TCP, that would autonomously handle any data that fails to transfer within a file and kind of retry without any intervention or stopping the transfer. And that's it. So thanks for listening. You made it this far.